Yesterday's class is the last one that's going to be on the test tomorrow. Gives you some time to study. The exam reviews, I had somebody in my office after class yesterday and I was explaining some things. So I actually did some modification of those to try and explain some of the answers better. But if you're still having trouble with understanding some of the answers, just email me and let me know. So I modified them and reposted them. So like I said, it explains some of the things a little better. I wrote the first part of the exam. It's the long answer math thing. Well, you have topics that include colligative properties, finding rate laws from concentration changes, finding K values from integrated rate laws, the Arrhenius equation, half-lives. There's a lot of possible math questions. And then there are 5 questions. The total is 70 points. I haven't written the multiple choice part yet, but you've got multiple choice review section, so it'll look like that. Some of the multiple choice questions are more conceptual, like define what this thing is. There are a few that have simple math questions on them. There will be 15 questions. They will be 2 points apiece, so that's 30, unless I decide that I need to. I haven't added points to the long answer part yet, and if I decide that 70 points is too much for that, I may cut it down and then increase the multiple choice ones to like 3 points a piece or something. I'm not quite sure yet. I have to work out the answer keys. I wrote the test, don't have answer keys, before I can figure out how many points make sense. But I do know there's 5 of those, and there will be 15 multiple choice, and as I pointed out yesterday in class, there will be a bonus on the multiple choice, and the bonus is simply, can you convert from one concentration unit to another? We missed you yesterday, Xavier. There was nobody to answer questions. I don't mean to embarrass you, I'm sorry. So, we're going to start chapter 15 today. And what we introduced today okay, I'm like, why do I have that? That's from last year. What we introduced today will carry through all the way through chapter 19. So we're just going to apply it to numerous different things over the course of the next several chapters. Now, I kind of introduced this yesterday because they introduce it in chapter 14 and say, this is how we solve this rate equation, but we don't really spend in depth on it. So I need to go a little more in depth on the concept of equilibrium. Equilibrium is important to us because when a reaction is occurring and concentrations are constantly changing, we can't really figure out what's going on. At equilibrium, we have a chance to monitor exactly what's going on in the reaction. Equilibrium only applies to reversible reactions. Reversible reactions are ones in which the difference between the activation energy of reactants going to products is not that different from the activation energy of products going to reactants. So it's not like we've got this hill for reactants going to products, but products going to reactants is huge. We want something that's fairly similar, because that way we can get back as well as going forward. So a reversible reaction is one in which once we start making products, the products will start going in reverse and making reactants. So when I say forward reaction, I mean reactants going to products. When I say reverse reaction, I mean products going back to reactants. And the products will begin to react and go back and make reactants again until the rate of the forward reaction equals the rate of the reverse reaction. So every reactant that makes a product is matched by a product making a reactant. So the rates of the reaction forward of reactants going to products is now the same as the rate of the reverse of products going to reactants. So there's my equation. At equilibrium, rate forward equals rate reverse. So it doesn't look like that on this picture. What they should have done was overlap the red and the blue and made a purple line there. But at that point, the forward reaction, this is the decomposition of ammonia, and the reverse is making ammonia back. And NH3 goes down and the rate slows down. The reverse reaction rate increases as we get more products until the two of them equal. So this is the reaction that I had. So at equilibrium, we have a situation in which for every forward reaction, we have a reverse reaction. And the reaction will look like it stopped. The reaction appears to have completely stopped. I'm going to skip forward a couple of slides. This is called the dynamic equilibrium because things are still moving. The reaction appears to have stopped, but it has not stopped. An equivalent metaphor to this is a club with a certain capacity. So many people, 200 people can be in here. Doesn't mean it's always the same 200 people. When one person comes out, another one can go in. So there's always 200, but not always the same 200. It's the same with the dynamic equilibrium. There's a certain number of reactants and a certain number of products, but they don't have to be exactly the same molecules. So we know equilibrium has been reached when past that, everything looks exactly the same. So I start with all of these, whatever that's supposed to be, H2O maybe? And it breaks down to give me, in this case, H2 and an oxygen atom. So I start with all H2O. By B, I'm seeing one of them break apart. By C, I've seen two of them break apart. But look at D. D is exactly the same as C. Because D is exactly the same as C, it means I reached equilibrium at C. And everything after that will look exactly like C. If the equilibrium had been established in panel B, then everything would simply look exactly like B does. Now we know it doesn't stop. We know it's not always the same molecules because we have ways of tracking. We can put in what are known as tracer molecules. We put in one that has a radioactive element in it. And we can see that that radioactive element can go back and forth between products and reactants. So we know this is a dynamic equilibrium. We know this is what happens, even though it looks like the reaction has stopped. So this is the equilibrium point. The equilibrium point is the point in which rate forward equals rate reverse, and the reaction looks like it is stopped, and the concentration of both reactants and products becomes a constant. So this is the reaction of two iodine atoms making I2. I create I2. I remove I until those concentrations become a constant. And they will be a constant forever if I don't touch that reaction. And this is what happened. The two rates became equal. So the rate forward equaled the rate reverse. Now we used this yesterday in establishing a rate law for something in which the first reaction went fast. We allow it to go fast enough until the concentrations of the reactants and products become a constant. This was a problem yesterday because we had a rate law based on a second step that included an intermediate. And intermediates are formed and then break down again. So we don't know what their concentration is. But now we know at equilibrium, the concentration remains the same. And therefore, we can figure out what the concentration is of that intermediate. Provided the second step is slow enough that it's not immediately eating up that intermediate, we now know how much we made because we now know that the concentration at equilibrium becomes a constant. I really wish I could find this not cropped. We're going to talk about how these rates are done. So for example, for this guy, the rate forward is K times I squared. For reverse, that's K forward. This is K reverse, I2. Now KF I squared equals KR I2. The rate are equal. The rate constant is different. Like I said, I wish I could found this not cropped. But it says, are the rate constants equal at equilibrium? No, only the rates are equal. K is a constant for the forward, and it's a different constant for the reverse. So rate constants are not always equal. Most of the time, they will not be. So if my rate forward is KFI2, and my rate reverse is I squared, and reverse is KRI2, then those two things have to be equal. ChemCat, 2 steps forward, 2 steps back. In this case, it's actually 2 steps forward, but only 1 step back because I only have one product. So KF I squared equals KR I2. I'm going to rearrange and put all the K's on the left side and all the I's on the right. So now KF over KR equals I2 divided by I squared. KF over KR is a new constant. K, rate constant, is a small k. We've run out of letters in the alphabet. We've run out of letters in our alphabet. We've run out of letters in the Greek alphabet. So we have to use the same letter over and over. If you go back and you study for the test tomorrow, you'll find that the small k is also used in Henry's law. Just represents a constant. It's not the same as the rate constant. It's just a constant. Small k here represents the rate constant. Large K is now the ratio of the forward to the reverse rate constants. Large K is my equilibrium constant. Now, unlike rate constants, equilibrium constant is stoichiometric. So if I have A moles of A plus B moles of B going to C moles of C plus D moles of D, it is products over reactants, and it is C to the C power, D to the D power, A to the A power, B to the B power. It is stoichiometric. So we don't have to sit here and try and figure out what the exponents are like we had to, like you had to. I cheat, I use the answer key. We don't have to figure out what those values are. It is purely stoichiometric. I like stoichiometry, and I cannot lie. The American Chemical Society, ACS, actually has a mascot, and because we talk about moles, their mascot is a mole. So that is the ACS mascot, and he likes stoichiometry because it's easier than trying to find the values for the rate constants. So if I'm going to write an equilibrium constant expression, it is just products over reactants, concentrations of PCl3 times Cl2 divided by concentration of PCl5. For the second one, where I have 2 H2Os and 2 H pluses, those stoichiometric coefficients become exponents. So H2O squared, 2H plus, OH minus, both of those squared. Okay. Now, in reality, that is an incorrect equilibrium constant. We'll explain why later. But for now, we're just products over reactants. Okay, so equilibrium constant, okay? It is a rate constant was purely based on what our initial concentrations were of our reactants. K, our rate constant, is independent of initial concentrations. I can get the same K value whether I start with all reactants and no products, I can start with N2 and H2 and reach a point where they're all constant. And there is a K value there. I can start with all products and go to reactants and go backwards. Or I can start with a mixture of reactants and products. The K value will be exactly the same, whether I start with all reactants, all products, or a mixture of reactants and products. Okay, so rate law. Rate law tells us how fast the reaction goes. It's basically telling us how fast equilibrium is reached. How fast is the reaction going to go until it reaches the point where it looks like it's stopped. So what does the equilibrium constant tell us? Well, the equilibrium constant is going to tell us how well the reaction goes. Not how fast it goes, but how well it goes. How far to completion does it go? Do we get a bunch of products and almost no reactants at the end? Or do I get very few products and it stays mostly reactants? So the equilibrium constant tells us how far to completion. Completion meaning start with 100% reactants and end up with 100% products. This tells us how far to completion the reaction goes. There are some reactions that do not have equilibrium constants. They go to 100% completion. If they go to 100% completion, they are not reversible reactions. So I can't have an equilibrium constant. Can you reach it? No. I was going to say, does somebody need to get it from the back? So only ones in which we find an equilibrium setup where there are reactants and products are we going to have an equilibrium constant, and it'll tell us how many products we have versus how many reactants. So if I have a very large value of K, products are on the top, reactants are on the bottom, so a very large value of K means I've got a lot of products. So at the end of the reaction, I'm probably mostly product. But if I have a very small value of K, that means the reaction doesn't go very well at all, and I'm going to still have mostly reactant at the end of the process. Now, K will probably never be equal to 1, because to be equal to 1, all of those concentrations and those squares and all of that sort of stuff has to be equal to 1. We'll look at a couple of things Thursday or Friday, I'm not sure which day, where we can set it equal to 1, but for the most part, K is never equal to 1. So I'm not going to have the exact amount in the numerator and the exact amount in the numerator, but I can get an intermediate value where I have an almost equal amount of things. Usually, an intermediate value of K that gives us a good mix of reactants and products is considered to be between 1/1000th to 1,000. 1 times 10 to the minus 3 to 1 times 10 to the positive 3. In that range, we consider to have a good mixture of reactants and products when we're done. So K is basically telling us how well the reaction proceeds. Not how fast it goes, but how good is that reaction. So very small, reaction proceeds hardly at all. Very large, it goes to nearly completion. And there's our 10 to the minus 3 to 10 to the positive 3, where we get both products and reactants at equilibrium. So I've got an equilibrium constant that's 1.5 times 10 to the minus 5. Okay, we're not going to have, when we look at the equilibrium constant, we're not going to have decimals for the most part. We're going to list things in terms of scientific notation. Then we can look at the exponent. I've got an exponent of 10 to the minus 5. That is 0.0000015. Big or small? Pretty small, right? That means this reaction is crap. I'm not going to get a lot of B for this reaction. It's going to stay mostly A. So at equilibrium, this reaction is still going to be mostly A, because that extremely small value means I have few products. Okay, now on the other hand, the reaction of hydrogen with sulfur, H2S. Anybody know what hydrogen sulfide is? Of course, Xavier. Xavier got a 5 on his AP. I'm embarrassing him. So don't feel bad if you don't know the answers, is what I'm trying to say. If you've never had chemistry before, if you don't know these answers, it's fine. Hydrogen sulfide is the smell of rotten eggs. Egg yolks have sulfur in them. As they go bad, they develop H2S. Now, look at that equilibrium constant, 1.1 times 10 to the positive 7. That's a really good K, which means that that rotten egg smell really likes to be produced. It's very easy to produce hydrogen sulfide. SO2Cl2 goes to SO2 and Cl2. You would think that with a big messy molecule like that, it might fall apart fairly easily and give me SO2 and Cl2. But it doesn't, because its reaction is, its equilibrium concentration is really small. So for A, I get a large K, I'm going to get mostly products. For B, I get a small value, so it's mostly reactants. Now look at C. C is the opposite of A. If A is very large, what should I expect from C? Okay, if I've got H2 going and S2 going to H2S, and it really likes to do that, how easy is it going to be to get H2S to go back? Not very well at all, is it? So the reaction of H2S going back to H2 and S2 is going to be pretty bad. I'm going to have mostly reactants. Now, your book likes to ask, does this favor the forward reaction or does it favor the reverse reaction? Forward reaction being favored means I'm making products. That's a large K value. Favoring the reverse reaction means that what few products I do make tend to easily go back to the reactants, and therefore it's favoring the reverse reaction. So in addition to saying I'm making a lot of product or I'm making a lot of reactant, we can say that a large K favors the forward reaction, whereas a small k favors the reverse reaction. And I had my calculator on because I was checking something, but then I noticed A and C are at 2 different temperatures. In reality, if A and C were at the same temperature, the value for C would simply be 1 over the value for A, because we're just flipping our reactants and products. But they're at different temperatures, so not the same. Okay, so I didn't put any animations in here, so let's try and put some animations in here, just because it's easier to see one thing at a time than to look at all of it. Okay, so I have phosphorus pentachloride, PCl5, decomposing to PCl3, phosphorus trichloride, and chlorine gas. First and foremost, Just like rate constants, equilibrium constants depend on molarity. This is giving me moles, not molarity. So the first thing I have to do is convert those moles to molarity. It's just moles divided by liters. If this was in a 1 liter container, then the molarity would be the moles, but it's in a 2 liter container. So the molarity of PCl3 is 0.188 divided by 2 liters, or 0.094. The concentration of PCl5 is 0.98 divided by 2, or 0.49. But they just give me PCl5 and PCl3. What's going on with chlorine? Well, we have to make an assumption here. And the assumption here is that the reaction started with just PCl5. It's telling us that PCl5 decomposes. So our assumption is that we started with all PCl5. And if that's the case, for every 1 PCl3 we made 1 Cl2, which means that the concentration of Cl2 would be the same as the concentration of PCl3, or 0.094. This is an assumption I have to make from the way the question is worded. This decomposes, so I'm making the assumption that I started with all reactants and no products. So then, K will be PCl3 times Cl2 divided by PCl5, or 0.094 times 0.094 divided by 0.49, and the answer is 0.180. Now, rate constants had units. The rate constant unit was rate, molarity per second, divided by molarity raised to the power of the total order of the reaction. So it was molarity per second for 0. It was 1 over seconds for first order. It was 1 over molarity times seconds for second order. What the unit is for the equilibrium constant depends on exactly what I have for exponents in all of this. How many reactants do I have? What are their exponents? How many products do I have? What are their exponents? So because it gets complicated, we're never going to give the equilibrium constant a unit. We're just going to say it's unitless. Saves us from having to mess. This would be molarity times molarity divided by molarity. The unit would be molarity, but we're just going to ignore all units when it comes to equilibrium constants. So what I've calculated here, you can see the equilibrium constant K sub C in the question. What I calculated was K sub C, which means it is the equilibrium constant that is found from molarity, from concentrations. Every time I wrote equilibrium, I stuck an extra I in it. I don't know why. So if I look at some of the things I worked on, everything I've looked at so far is gases, and I'm saying I'm doing a concentration, which is perfectly fine. I can do concentrations with gases. But sometimes an easier way to solve for K, if I have a gas, is not to look for a concentration, but to look for the pressure the gas is exerting. So we have something called K sub P. K sub P is the equilibrium constant found from pressure. Hey, I spelled equilibrium right there. So K sub C is my molarity. K sub P will be pressure. It sets up exactly the same way. If I have 2 CO, O2 is 2 CO2, then my K sub C would be CO2 squared divided by CO squared times O2. I'm simply going to replace every one of those concentrations with a partial pressure. And I now have Kp equals pressure of CO2 squared divided by pressure of CO squared times pressure of O2. Now, it turns out that K sub C can be done not just for all the ones I did where they were gases, but it can be a mixture of things. As long as there's something I can get a concentration from, I can do a K sub C. K sub P can only be done with all of your reactions and products that are going into your K value being pressures. So this only works if everything's a gas. So K sub C actually becomes a little more convenient for us because we can mix gases and solutions and other things. But it sets up exactly the same way. We're just going to use pressure instead of concentration. So how do Kc and Kp compare? Had to put something up in celebration of Toy Story 5 coming out. I'll be perfectly honest, I haven't seen anything since Toy Story 1. You see things like that when your kids are young. My daughter's not that much older than you. She's only 24. So we saw Toy Story, but they're not Toy Story 5. But Toy Story 5's out, so I have to do a Toy Story thing. So let's look at how concentration compares to pressure. We'll go to the ideal gas law. Ideal gas law is PV equals nRT. But I move the V to the other side, and I get P equals N over V times RT. Well, N over V is a concentration. It's a molarity. So pressure is related to molarity, or molarity is related to pressure. I just rearranged it and said, this is the molarity, capital M, equals pressure divided by RT. So if I have a K sub C where I have concentrations, I can put pressure in directly. So I could take all of those guys and replace concentrations with P. My Kp would be the pressure of C times the pressure of D divided by the pressure of A times the pressure of B. But this just put pressures in. And molarity is actually pressure divided by RT. I left out the RT. So they're actually P over RT for every one of those. But I can pull the RTs out. I have 1 over RT to the C, 1 over RT to the D, divided by 1 over RT to the A, and 1 over RT to the B. So I'm just going to pull the RTs out. Now, this is my K sub P. But I have all these factors. Oops, I forgot a 1. Of RTs. Combine them all together, and I get 1 over RT, C plus D, divided by 1 over RT, A plus B. But I don't want 1 over RT, I want just RT, so I'm going to flip it. And I'm going to get RT to the A plus B over RT to the C plus D. And I'm going to call this a change in RT. How does RT of the reactants compare to RT of the products? So I end up with this equation, that Kp equals Kc times RT to the delta N, where delta N is the number of moles of product minus the number of moles of reactant. So if I have more product than I have reactant, Kp should be bigger. If I have less product than reactants, Kp should be smaller. Kp equals Kc when the same number of moles is present on both sides of the reaction. So I have 1 mole of gas on each side there. So Kp equals Kc. I have 2 moles of gas and 2 moles of gas, so Kp equals Kc. I have 4 moles of gas and 4 moles of gas. So for those 3 reactions, Kp equals K sub C. So equilibrium between nitrogen gas, okay, this is the Haber process, and it's used a lot in examples in Gen Chem. It's a fairly simple, straightforward equilibrium that is not a 1-to-1-to-1 stoichiometry. So N2 plus 3H2 goes to 2NH3. Kp is 6.8 times 10 to the 5. So now we're going to go backwards here. If Kp equals Kc times RT over delta to the delta n, then Kc is going to be Kp divided by RT to the delta n. Well, delta n here is 2 minus 1 plus 3, or negative 2. I'm going down by 2 moles of gas. Now, R is just my ideal gas constant, 0.08206. Okay. On your equation sheet, you are given 2 values of R. 0.08206 is used when we're dealing with gases and pressures. It's used here. It's used in osmotic pressure. When we're dealing with energies, like in the activation energy equation, it's the 8.314. So the units are there. If the R value on your equation sheet says liter atmospheres, use it for pressure. If it says joules, use it for energy. So my Kc will equal Kp divided by RT to the negative 2. Or I can take the 0.08206 times 298 as a negative 2 and bring it up to the numerator as a positive 2. And 0.08206 times 298 is 24.45. So I brought it up to the numerator as a square. So K sub C is 4.1 times 10 to the 8th. Now I said when there are more products than reactants, K sub P is going to be bigger than K sub C. When there's fewer reactions than there are products, K sub P is going to be smaller than K sub C. So we see our K sub P is smaller than our K sub C because we have fewer moles of gas on the product side. Okay, if we stop and think about this, K sub P here is smaller than K sub C. Pressure. I have a relationship between pressure and the number of moles of gas. It's called, no, it doesn't, that one doesn't have a name. Gay-Lussac's law is pressure to volume. This is one of the gas laws, but it doesn't have a name. But pressure is related to the number of moles. If I go from 4 moles of gas to 2 moles of gas, I'm actually reducing the pressure because I have fewer moles of gas. If I have fewer moles of gas, then it's going to adjust how this reaction is going to want to go. And it's not going to necessarily want to go forward because it doesn't want those fewer moles of gas. So the pressure on the product side is lower because I have fewer moles of gas than it is on the reactant side. And if the pressure is lower on the product side than the reactant side, then my K value becomes smaller when we do it with pressure. Okay, N2O4 breaks down to 2NO2. The equilibrium pressures of N2O and NO2 are given in atmospheres. Again, whether I give a pressure here in torr or in atmosphere is unimportant because the K values are unitless. We prefer atmospheres if we're going to convert between, no, we have to have atmospheres if we're going to convert between K and P, Kc and Kp, because R is in atmospheres. So equilibrium constant for this is simply NO2 squared over N2O4, or 0.512 squared divided by 1.74, and it's 0.5151. This isn't a large K sub P, but it's not really a small K sub P either. When I do this, I still leave a fair amount of N2O4 in that form, and I get a pretty good mixture. NO2 is brown. As I produce this, I will see a brown color being produced. If I were to do the reverse reaction, and I started with the brown color would dissipate, but it would never completely go away because it would be still a good mixture of NO2 with the N2O4, which is colorless. So this is a good mixture when I get through of both the reactant and the product. Okay, so this says these were all solutions or gases. The answer is actually everything we did was gases. But we can do concentrations of solutions. So we can do a case of C for a solution. We can do a case of P for a solution or a gas. No, I guess it's the other way around. Okay, I'm not having a good morning this morning. Have you noticed? Case of P can be done only for gases. Case of C can be done for solutions or gases. But what about this guy? H2O is a liquid. H plus and OH minus are solutions. That little AQ next to them tells me it's a solution. But H2O is a liquid. If I have a heterogeneous equilibrium, for example, the decomposition of limestone, calcium carbonate, to produce CaO and CO2. CaCO3 and CaO are solids. Limestone is just a rock you can dig up in a lot of different places. CaO is lime. It's the white stuff they use to make the lines on the football fields. And it's created by heating up CaCO3 and driving off CO2 gas. Again, nothing that has to do with this. It's just you should know that these chemicals actually have a place in real life. What do I do with this? Is the equilibrium constant CO2 times CaO divided by CaCO3? Well, it turns out I can't have a concentration or a pressure for a solid. Obviously can't have a pressure for a solid. But I can't have a concentration for a solid either. Why? Well, for any reaction where we're going from reactants to products, the concentration is changing during the course of the reaction. How does the concentration of a solid change during the course of a reaction? Well, it turns out it doesn't. What would the molar concentration of a solid be? How many moles per liter are there of a solid? Well, we know two things about solids. We know their density and we know their molar masses. So concentration times molar mass would equal a density. Density is a constant. Molar mass is a constant, which means concentration, moles per liter, has to be a constant. It can't change because it's a function of the molar mass and the density. So if density is a constant and the molar mass is a constant, the concentration must be a constant. Therefore, I cannot have a concentration change during the course of a reaction that includes a solid. Now, that doesn't mean the quantity of solid I have doesn't change. I can take some of that solid and put it into solution in the process of the reaction, like taking NaCl solid and making Na plus and Cl minus in solution. I can certainly change the amount of solid I have. But I want a concentration, and concentrations of solids do not change. So if the concentration can't change, I can't put it in the equilibrium constant. So I'm going to take CaO out and CaCO3 out. They would have K values that would then be added to or added into the equilibrium constant. We replace CaO with some constant value. We replace CaCO3 with some constant value. Those constants would get included into the case of C, and my case of C simply becomes CO2. So the only thing that ended up in my case of C was my gas. So if I go back to, oh, I'll come back to that then. Let's do one more slide. Okay. So the equilibrium expression for this reaction is simply K sub C equals CO2. Only include things that say a G or an AQ when you're doing an equilibrium constant. And the same thing is true for pure liquids. Pure liquids, the same thing. They have a molar mass, they have a density, their concentrations cannot change. So if I go back to that very first slide I did with writing things, that should not be in there. Actually, that's upside down, isn't it? I don't know why I did this upside down. This should be up here, and this should be down here. Okay, so obviously I'm not just having a bad day today, I was having a bad day yesterday, last night when I was doing this. So in reality, H2O can't be included. So the equilibrium constant for that is simply H plus squared times OH minus squared. So when you are doing an equilibrium constant, when you learned in 1127 to write a complete balanced equation, we said you should include the states, but then we mostly ignored the states. Now we can't ignore the states, because in an equilibrium constant, only the things that say G for gas or AQ for an aqueous solution can be included in the equilibrium constant. Okay, so here we go with that one that I had before, and I left out the H2O. I can't include that because it's a pure liquid. Now, you may say, well, it's not a pure liquid because it's got all these things in it, but the water itself is pure. The other things are solutes in the solvent, and the water solvent is pure. Okay, now let's take a look at a comparison between acetylene making benzene and benzene making acetylene. Acetylene is welding gas. That carbon-carbon bond is a triple bond, so it's got a lot of energy in it, which is why welding torches are so hot. Benzene is a solvent. You can buy it like in Home Depot. Highly toxic, highly nasty things, but it's a solvent for oil and grease and things like that. And I can convert acetylene into benzene and write an equilibrium constant. But benzene does not go into it because it's a liquid. So okay, obviously, you can write this when you do your evaluation of me. I'm having a bad day. Okay, so benzene does not go in, so acetylene goes in. So it's 1 over, because there's nothing in the numerator, C2H3 cubed. In reverse, there is no denominator, because the denominator is a liquid. So it's just C2H2 cubed. So what are my rules for K? Well, if I reverse a reaction, I'm obviously flipping the equilibrium constant. That's one of my rules. If K is B over A, for a reaction where A goes to B, then the reverse reaction will be the inverse, the multiplicative inverse. K is a multiplicative function, which means the multiplicative inverse is 1 over, which means additions become multiplications. So multiplicative inverse, 1 over K. if I multiply the reaction by some stoichiometric coefficient, then multiplication, I would now have two B's, so B times B over A times A, or B squared over A squared, a stoichiometric coefficient out front becomes an exponent. With the 1/2, I multiply by 1/2, so it becomes the square root of B over the square root of A. So because it's multiplication, when I put in a stoichiometric coefficient, that becomes that times that, not that plus that, and I get a square or a 1/2 or a cube or whatever it is that I have. If I add two reactions together, again, multiplicative, I will multiply the K values. So adding the reaction multiplies my K because it's multiplicative. So I write the reaction for A, and it's N2O squared divided by N2 squared times O2. For B, it's N2O divided by I really apparently had a bad day when I was doing this. Times N2 times O2 to the 1/2. Now, to get from A to B, I divided by 2. So I'm going to take the square root of it. I'm going to take that to 1/2. So dividing by 2 is the same as multiplying by 1/2. So my K value then becomes taken to a power of 1/2, and it becomes the square root of A. Okay, so now I have two equations. NO plus 1/2 BR2 goes to NOBR, and then NOBR goes to N2 plus O2 plus BR2. Okay, this is a two-step reaction for two NOs going to N2 plus O2. It has a catalyst. The catalyst is BR2. It has an intermediate of NOBR. But we don't really care at this point that they have intermediates or not, or catalysts, because they're going to come out in the end. So how do I get from the first equation to the last equation? Well, the first equation has an NO in it, but the last equation has two NOs. So I'm going to have to multiply that first equation by 2, which squares my K. So 2NO plus BR2 goes to 2NOBR. My K now becomes 1.99. Now my second equation, I'm not going to need to do anything with, because 2NOBR are going to cancel 2NOBR, and a BR2 is going to cancel a BR2, and I'm going to be left with just the N2 and the O2. So I don't need to do anything to the second equation. I can leave it as it is. Now you can see that the first reaction of making NOBR is so-so. But once you made NOBR, it really likes to make N2 and O2. Look at the size of that K value. I'm going to get a lot of product out of that. So now I'm going to add the two equations together. My catalyst of BR2 and my intermediate of NOBR cancel. Again, we only have products and reactants in here. And I'm going to get my 2NO goes to N2 plus O2, which is what I'm looking for. And when I add the two equations, I multiply my Ks. So 1.99 times 1.06 times 10 to the 30th. The K, overall K for this two-step reaction is 2.11 times 10 to the 30th. Okay, now, Kc doesn't change. Whether I start with all products, I start with all reactants, or I start with a mixture of things, the equilibrium constant is a constant. It doesn't change. But the equilibrium constant is not the same as the equilibrium concentrations, the position of the equilibrium. So we can see that 1 started with all reactants and no products, 2 started with all products and no reactants, 3 started with a mixture of both, but my K value for every single one of them is 6.02 times 10 to the minus 2. But the concentrations are extremely different for each one. So equilibrium constant doesn't change, but the equilibrium position, how much I have left at equilibrium, is dependent on my initial concentrations. So K sub C is not, K sub P are not dependent on initial conditions, but what I get for final concentrations or final pressures is. So Kp doesn't change with pressure, Kc doesn't change with concentration. What it does change with is temperature. Our rate constants change with temperature. So our K value is going to change with temperature. Forward reactions tend to go better when they're hot, sometimes. We tend to think of reactions going better when they're hot, but that isn't always true. To determine whether or not my equilibrium improves, I get more product, or I get fewer products, depends on whether the reaction is exothermic or endothermic. So, I couldn't find one for exothermic, but I found this for endothermic reactions. Why do I have no volume? Okay, I don't know why I have no volume. Okay, but we're at equilibrium here. If I change the temperature and I add more heat, in an endothermic reaction, heat is a reactant. It goes into the system, so it's considered to be a reactant. So if I add heat, I'm going to push things toward the reactant side because it says the volume's up. Okay. Because heat is now a reactant, I've got more reactants now. More reactants will then allow it to produce more product until I reach equilibrium again. So in an endothermic reaction, adding heat is adding a reactant. It gives me more reactants and then allows a new equilibrium to be produced, which has more products. So in general, endothermic reactions like high heat, they need that energy. They will do better at a high temperature. On the other hand, an exothermic reaction is trying to release its heat. And you know how it's harder to sweat when it's 100 degrees out than it is when it's 70 degrees out? Same for the exothermic reaction. It's harder for it to release its heat when it's in a hot surrounding. So exothermic reactions tend to do better at low temperatures. We will get back to this concept in chapter 18. Okay, enthalpy of a reaction from last semester is the sum of the enthalpies of the products minus the enthalpies of the reactants. Again, we'll get back to this in chapter 18. But they give me a reaction in which ammonia is reacting with oxygen to make N2 and H2O. My delta H is products minus reactants. N2 is an element, it's 0. O2 is an element, it's 0. So it just becomes H2O minus NH3. So negative 241.8 minus negative 46.1 gives me a delta H of the reaction of negative 195.7. This reaction is exothermic. So increasing the temperature of this reaction is a bad thing. This reaction prefers to go at lower temperatures. Okay, I planned this to be a little bit short, so let's take a 5-minute break. And Then I'll answer any questions, do a quick review for the exam tomorrow. Let's review a little bit in the 20 minutes I have left as to what to expect on the exam. Okay, so your equation sheet is here. You will get a copy of that. One side of the equation sheet, the other side the periodic table. We're not going to expect you to memorize all these things. I am a firm believer, unlike some of the other faculty members that teach Gen Chem, that memorization is a waste of brain space. And they tell us we're supposed to teach you critical thinking skills. But how can we teach you critical thinking skills when you're spending all your time just memorizing stuff? That's why I hate biology. Biology is too much memorization. I want to be able to say, okay, this does this, and this is what I can expect, not, okay, I just memorized that list. So I like to make sure that you have as much as possible for the test. So you have your constants, both the values of R, liter atmospheres is for gases, joules is for energy. It's got the conversion from Celsius to Kelvin. Make sure everything you do is in kelvins. Conversion of atmospheres in torr. It's got Avogadro's number here, but we don't need that for this. And the other two, the kW, the other three, ampere and F, are for later. This covers all of the semester. But under equations, your first one is Henry's law, C equals Kp. In the review problem that does Henry's law, I say, unless you're specifically asked, you don't have to solve for K. It's like back when you did gas laws. You could simply say PV1 equals PV2, or V over T1 equals V over T2. You didn't have to find what that constant was. You don't have to find what that constant is. You can just say C over P is a constant. Molarity divided by pressure is always a constant in Henry's law. Okay, the next one is the vapor pressure, Raoult's law. Just remember what units you use for each thing. Chi is a mole fraction, and it's the mole fraction of the solvent, not the solute. Boiling point elevation and freezing point depression are there, including the K values for those. And notice they both have I in front of them. I is your Van't Hoff factor. If something is all carbons and hydrogens and maybe some oxygens, I is just 1. I only has a value if it's an ionic compound. And then I is the value of the ions. So NaCl, NaCl, I is 2. CaCl2, calcium, 2 chlorines, I is 3. Just be careful that if you get something like Mg3PO4 sub 2, PO4 is a polyatomic. Don't separate the phosphorus and the oxygen. Mg3PO4 sub 2 would be 3 manganese, 2 phosphates, 5 total particles. Pi equals I MRT. Oh, and boiling point elevation, freezing point depression, use molality, the moles per kilogram of solvent, not solution. The next one is my osmotic pressure, and big M is molarity. Again, it's got an I value in there. The next line is the Arrhenius equation. The Arrhenius equation is usually used when you do a reaction at 2 different temperatures and the K value changes to find that barrier, that activation energy barrier, by the natural log of the 2 Ks ratioed and times 1 over T1 minus 1 over T2. If you do it this way with K2 over K1 and T1 minus T2, you should get the correct answer. If you get a negative value, it means something's backwards. Just swap your temperatures or something. Because E sub A is positive, it's an endothermic process, it's energy you have to add. Okay, the next one down is an equilibrium one that we will be doing a little bit later, but then we have our 3 integrated rate laws. So one thing that is not on here is how to write a rate law depending on the order. You have to find the order of the reaction from concentrations, and then the rate law is just K times the concentration raised to that power. So that is not on there. But your integrated rate laws and your half-life equations are, and they are simply in order: 0 order integrated rate law, 0 order half-life. First order integrated rate law, first order half-life. Second order integrated rate law, second order half-life. Everything else below that is for further chapters, but those things are all up there. So if we look at the exam reviews, you can see under solutions, we have Henry's law. We have calculating concentrations, molarities, moles per liter, molality, moles of solute per kilogram of solvent, mole fraction, moles of solute versus total moles, except for what we usually do. It's not moles of solute, it is moles of solvent. For vapor pressure, we want to use moles of solvent. Mass percent, just grams of solute over total grams. I could do grams of solute over total milliliters, milliliters over milliliters, and I would get a mass percent here, a mass to volume percent, or a volume to volume percent. They're all calculated the same way. So examples of how to find the molarity, how to find the mass percent, how to find the mole fraction, how to find the molality. Now, if we want to convert between one and the other, we need to know exactly what it is that we need for each one of those things. So in the multiple choice practice problems, in the bonus, it shows you for the first one, we're giving volume to volume percent, milliliters to milliliters. It's given a density of the ethanol, and it wants to know molarity. Well, volume to volume percent means 13.5 milliliters of ethanol in 100 milliliters of solution, or 13.5 times 10, or 135 milliliters of ethanol per liter of solution. Then I used the density of ethanol to convert to grams of ethanol, converted the grams of ethanol to moles of ethanol, and then divided moles by liters. So I had to look to see what I had. What things do I have? Well, I have a volume of solution already, 100 milliliters, and I just need to convert those milliliters of ethanol to eventually moles. For the second one, it says molality needs to be found from a concentration of 0.420. The density of the solution is 1.05 times 10 to the third. Now I have to convert the entire solution to grams. So I take 1 liter of solution and multiply it by 1.05 times 10 to the third grams per liter. That gives me 1.05 times 10 to the third, or 1,050 grams, or 1.050 kilograms. Then I found grams of salt, because for this, for finding molality from molarity, I want only the solvent. So I have to remove the solute. So I got the solution into grams and then subtracted off the grams that were salt. Now I have the grams of just the solvent. And they gave me moles already. So the most complicated part here was taking liters, converting them to grams for the solution, and then converting moles to grams for the solute, and subtracting the two. So you need to know how each one of these is created. Like I said, that's a bonus question. You don't have to do it, but it's there. Okay, so this one is fairly simple. It just says how much NaCl is in 156.2 grams of a solution. It's just, there is an answer one to this. I don't have the answer one open. It's just what is 15.5% of 156. Molality, again, finding that from mass percent, mass to mass. We want molality, so mass of solution is, right at this point, 100 mils. We can convert 7.5 to 75 and make the mass a liter. Convert the 7.5 grams in the 100 mils to moles and do moles per kilogram. Okay, colligative properties, we have several of them. You need to know how to calculate each one. All the equations are on there. You just need to remember which one to use. So adding a solute lowers the vapor pressure. We use Raoult's law. And in this case, as I said, chi is for your solvent, not your solute. Boiling point elevation, your equation is on the sheet. Just make sure your concentration is in molality. Freezing point depression, same thing. Neither one of these have I's in front of them, but they do have I's in front of them on the test. Osmotic pressure, right from the ideal gas law, pressure equals molarity times RT. And then my Van't Hoff factor is how many ions do I have there? So MgNO3, 1 mg, 2 NO3s, so that's 3. NaNO3, Na is 1 ion, NO3 is a second, that's a polyatomic, so there's only 2 there. C2H4OH2, that has nothing in it but carbon, hydrogen, and oxygen, that is non-ionic, so 1. Okay, then we moved into chapter 14. Rate expression isn't as important to us, but you should be able to know how these things relate. We introduced them and then went straight into rate laws. But if I have a rate expression that says one of the materials changes at a certain rate, how does the other one change? So if I have A, what happens to the rate? If I triple B, what happens to the rate? Or if I give you a rate of the reaction, that is with respect to B, what's the rate of the reaction? Well, B is a 1, so the rate of the reaction is just 1 of that, 7.42 times 10 to the minus 4. C, however, is twice as big, so the rate for C would be 1/2 of that. And the rate for A would be the same as the rate for B. Average rate, simply change of concentration between 2 points and change of time over 2 points. This is more important, how to find the rate law. By initial concentrations and initial rates, pick any 2 experiments, ratio the rates, ratio the concentrations that match, raise them to a power. That power is the order of your reaction with respect to that material. Once you have that, then you go put that into your rate law, and your rate is K times whatever power A is raised to. And then you solve with any one of the experiments for K. So in this case, I might take 2 and 1, and A doubles, and the rate doubles. So that's a 1-to-1 relationship, so N would be equal to 1. So my rate would simply be K times A, and then I would take any rate and any A and solve for K. There are answers to all of these. I'm just not showing them. If there's more than one reactant, do each one separately with a set of experiments where only one changes. So I'll pick experiments 1 and 2 because H2 stays the same to solve for NO, and I will use experiments 2 and 3 to solve for H2 because H2 is the only one that changes. I will find an N value for NO and an M value for H2, put them all together into the rate law, and solve for K. Okay, integrated rate law, as I said, these things are on the equation sheet. With the rate law from initial concentrations, the standard thing to do is to ask you for the orders of the reaction, what are the N and M values, and then ask you to find K. With an integrated rate law, you are told what the order of the reaction is already, because you have to know which integrated rate law to use. So straightforward, you solve for K. Then we have two things we can do once we've solved for K. One is to find the concentration of a material after a certain time. The other thing that we can do is find a half-life. Now, you should also be able to identify from a straight line what the order is. If the straight line is when you plot A, then you know it's zero order. And these come straight out of this integrated rate law. If it's natural log of A, it's first order. If it's 1 over A, it's second order. They come directly out of the integrated rate laws. Okay, this was calculating half-lives. And here's just a review. What is your rate law? What are your units of the rate constant? If I ask you on a test, calculate K and give the proper units, you should be able to give the proper units for K. Molarity per second divided by molarity raised to the power of the total order. The integrated rate law, the plot needed to find a linear plot, and the half-life. So this is just a review of pretty much everything. Recognize an energy diagram, be able to identify where is the activation energy, where is the enthalpy. So activation energy is from the start to the top of the hill. Enthalpy is from the start to the finish. And if I look at these things, reaction A is probably a pretty good reversible reaction because the values of E sub A are not that different. On the other hand, reaction B probably doesn't want to go forward. It probably only works at a very high temperature because of that huge E sub A. But a reverse reaction would be fairly simple for it. The Arrhenius equation, it's on the equation sheet. And it's simply solve for E sub A given 2 Ks and 2 Ts. Okay, finding second temperature is a little more complicated, so I ended up not putting it on the test, but you do need to use the Arrhenius equation. Now, if you look at the multiple choice, they're very different. The first one is a conceptual problem. What happens if I do this? Second one's a conceptual problem. Third one is just what would have the highest vapor pressure? Notice I've answered pure water because adding anything to water lowers the vapor pressure. Another conceptual, what's false? This one is a little bit of a math. This is using the I value, multiply your molarity times number of ions, figure out what the actual IM value is, and the highest IM value would have the lowest freezing point. There's my Henry's law. Henry's law is simple enough that I would put it on a multiple choice as opposed to a long answer. Just CP1 equals CP2. Now, the next one is a little bit different because this one says, I'm giving you a delta T. What is the I value? Because for Mg SO4, I was going to say CO3, SO4. I have an Mg, I have an SO4. That should be a value of 2. But when I plug all of the information it gives me into the equation and I solve for I, it's only 1.2. That's a pretty big difference. At a 0.1 molal solution, magnesium sulfate does not dissociate very well. Anybody know what magnesium sulfate is? It's Epsom salts. If you've ever used Epsom salts, you know it doesn't dissolve very well in water. Okay, units of K. For first order, for second order, whoops. Here's one where it says, if I have a plot versus time, which gives me a straight line of 0.0445, what is my rate expression? Well, the slope 0.0445 is my K value, but 1 over C2H4 indicates it's second order. So C2H4 squared. Okay, assuming a single step, my rate law will match my stoichiometry. So the rate law for this would be A2, B2. If we change concentrations, what happens to our K values? If I give you a rate expression, what does it tell you about the orders of the reactions? This is one where I compare, the rates. I have a rate of 0.2 for A. What is the rate of C? Well, it's 1/4 A equals C. So that's a mistake. This should be -1/4 A over T equals C over T. And yes, I know I didn't put the deltas in, but 1/4 or sorry. Or if I want to look at it the other way, that equals 1/4. So it should not be 0.1. It should be 0.05. I will fix this right now, and I will repost it. Okay, then if you continue down, I know that was the bell to leave. If you continue down, there's questions, again, on rates of change. There's questions on order from graphs. There's some questions on half-life. Now this one, I have 100 grams, which has a half-life of 10 years, which means at 0 time it's at 100 grams. At 10 years, it's at 50 grams. At 20 years, it's half of the 50 or 25. Some of these half-lives, you can just go by, this went down by a half, so its first half, it went down by a quarter, it went down by an eighth. Sometimes you don't even have to use the half-life equation. And I know class is over. So there's some stuff on activation energy and energy diagrams. There's some information on catalysts, and there's some information on mechanisms and finding intermediates and catalysts. Okay? So exam is in class tomorrow afternoon in lab, which gives you the full 3 hours. If you are taking it at CSD, I currently haven't seen any people that are saying that they're taking it there. Please just let me know. Okay, have a good night. Lab is up, pre-lab is up. You should be all set for all of that.